The universe we inhabit feels stable, anchored, and still. From our fragile vantage point on this spinning world, the cosmos appears as a majestic, silent clockwork. Stars wheel in predictable arcs across the night sky. Galaxies, those distant islands of light, seem frozen in an eternal tableau. This perception of stillness, however, is a profound illusion. We are not still. We are anything but still. Our planet hurtles around its star at 67,000 miles per hour. Our solar system in turn carousels around the galactic centre at a staggering 500,000 miles per hour. Even our own Milky Way galaxy is not a solitary traveller. It is part of a vast cosmic current, a river of galaxies all streaming through the intergalactic void. For decades we believed this motion was simply the result of the universe's initial expansion, the lingering momentum from the Big Bang. But then we discovered something else, a deviation in our path. A current flowing against the expected cosmic tide. Something is pulling us. We and everything for hundreds of millions of light years around us are being drawn by an unseen, incomprehensible force towards a single, mysterious point in the tapestry of space-time. We cannot see it clearly. It hides behind the blinding glare of our own galaxy. Yet, its gravitational summons is undeniable. Astronomers have given this anomaly a name that befits its enigma and its power, the Great Attractor. It is a ghost in the cosmic machine, a gravitational titan whose very existence seems to defy our most fundamental understanding of the universe. It is a mystery that doesn't just ask us to reconsider our place in the cosmos. It forces us to question whether the cosmos itself behaves the way we thought it did. The story of the Great Attractor is a detective story on the grandest possible scale, a search for a cosmic monster that breaks everything we know about space. Our journey into this mystery begins with the very concept of cosmic motion. For most of human history, we saw ourselves as the unmoving centre of creation. It took the Copernican revolution to set the Earth in motion, and centuries more to understand the Sun was just another star drifting within a larger stellar city we call the Milky Way. In the early 20th century, the brilliant mind of Albert Einstein gave us a new framework for understanding the universe: general relativity. His equations described gravity not as a force, but as the curvature of space-time itself. Massive objects warp the fabric of reality, and other objects simply follow these curves, like marbles rolling on a stretched rubber sheet. Initially, Einstein's equations suggested a dynamic universe, one that must either be expanding or contracting. This idea was so unsettling, so contrary to the prevailing wisdom of a static, eternal cosmos, that he introduced a fudge factor, the cosmological constant, to force his universe to stand still. But the universe refused to be caged by human assumptions. At the Mount Wilson Observatory in California, astronomer Edwin Hubble was undertaking a monumental task. He was measuring the distances to the faint, fuzzy nebulae that dotted the spaces between the stars. He discovered that these were not gas clouds within our own galaxy, but entire island universes, galaxies in their own right, millions of light years away. And then he found something that would forever shatter our concept of a placid cosmos. Almost every single one of these galaxies was moving away from us. Furthermore, the farther away a galaxy was, the faster it was receding. The universe was not static, it was expanding, a conclusion that sent shockwaves through the scientific world and even prompted Einstein to call his cosmological constant his greatest blunder. Hubble's law became the new bedrock of cosmology. It provided a beautiful, elegant picture of our universe. Imagine a loaf of raisin bread dough rising in an oven. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, it would appear that all the others are rushing away from it, with the most distant ones moving fastest. This is our universe. We're on one of those raisins. There is no centre to this expansion. It is happening everywhere at once. This expansion became known as the Hubble flow, the dominant motion governing the dance of galaxies. For a time, it seemed that all cosmic motion could be explained by this simple, majestic expansion, a symphony that began with the opening chord of the Big Bang. But science thrives on anomalies, on the subtle notes of discord that hint at a deeper, more complex reality. The first of these notes came not as a grand pronouncement, but as a persistent faint hiss. In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were working with a large horn antenna at Bell Labs in New Jersey. They were trying to conduct sensitive astronomical observations, but they were plagued by a persistent background noise, a microwave hiss that came from every direction in the sky, day and night, season after season. They checked their equipment, recalibrated their instruments, and even cleaned out pigeon droppings from the antenna, suspecting it might be the cause. The hiss remained. Unbeknownst to them, they had stumbled upon the most profound discovery in modern cosmology. They had found the afterglow of creation itself. This faint radiation, now known as the cosmic microwave background, or CMB, is the fossil light from the Big Bang. It is the light from a time when the universe was just a hot, dense, opaque fog, finally released to travel across the cosmos when the universe cooled enough for atoms to form. This discovery was monumental, providing direct evidence for the Big Bang theory. But the CMB was more than just proof. It was a gift to astronomers. It provided a universal backdrop, a definitive frame of reference against which all motion in the universe could be measured. Because the CMB permeates all of space, it represents a state of absolute rest relative to the expansion of the universe itself. Think of it like being in the middle of a perfectly still lake at dawn. The water's surface is your frame of reference. Any movement you make creates ripples. Similarly, by measuring our motion relative to the CMB, we could finally determine our true, absolute velocity through space. When astronomers performed this measurement, they found something astonishing. After subtracting the Earth's motion around the Sun and the Sun's motion around the galaxy, they found that our Milky Way galaxy and our entire local group of galaxies was still moving at a blistering 600 kilometers per second. This was not the random, chaotic motion of individual galaxies. This was a directed, coherent velocity. This was a peculiar velocity, a motion that could not be explained by the uniform expansion of the universe alone. The raisin bread was expanding, yes, but our raisin, and all the raisins nearby, were also being pulled sideways by some unseen hand. The Hubble flow was not the whole story. There was another current, a mysterious undertow, and it was dragging a colossal swathe of the universe towards an unknown destination. The hunt was on. In the 1980s, a team of 7 astronomers, who would become famously known as the Seven Samurai, embarked on an ambitious project to map the peculiar velocities of hundreds of galaxies. Led by figures like Alan Dressler and Sandra Faber, they methodically measured the distances and recessional speeds of galaxies in our cosmic neighbourhood. Their work was painstaking, a masterpiece of observational cosmology. They confirmed the earlier findings on a massive scale. It was not just our local group. Vast collections of galaxies, including the enormous Virgo cluster and the Hydra Centaurus supercluster, were all participating in this bulk flow. It was like discovering a continent-sized current in the middle of the ocean. By charting the direction of these galactic streams, they could triangulate the source of the gravitational disturbance. Their data all pointed to a single region of space, about 150 to 250 million light-years away, in the direction of the Centaurus constellation. There, somewhere in the void, lay an object or a collection of objects with a gravitational pull so immense that it was dominating the motion of a region of space hundreds of millions of light-years across. This was the location of the Great Attractor, but what could it possibly be? According to our understanding of gravity, the only thing that could exert such a pull is an enormous concentration of mass. The initial suspect was a supercluster of galaxies, a city of cities, far larger than any known before. The problem was, when astronomers pointed their optical telescopes towards this region of the sky, they saw almost nothing. A few stars, some dust, but certainly not the gargantuan collection of galaxies required to generate such a colossal gravitational field. The monster was hiding, and it was hiding in the most frustrating place imaginable, directly behind the clutter of our own home. The plane of the Milky Way galaxy, the bright dense band of stars and dust that stretches across our night sky, is a source of beauty and wonder. For astronomers looking outward, however, it is a veil of obstruction. This region is known as the zone of avoidance, or the zone of obscuration, because the sheer density of stars, gas and interstellar dust in our galactic disk blocks the light from whatever lies beyond. It's like trying to see a distant mountain range while standing in the middle of a blinding blizzard. The very structure of our home galaxy was shielding the identity of the cosmic titan that was reeling us in. For years, the Great Attractor remained a gravitational ghost, its existence inferred only by the wake it left in the flow of galaxies, its physical form a complete mystery. To understand the sheer scale of what we're dealing with, we need an analogy. Imagine the fabric of spacetime as a vast, near-flat, elastic sheet stretching out to infinity. The expansion of the universe is like the sheet itself, slowly and uniformly stretching in all directions. Galaxies are like small ball bearings resting on this sheet. According to the Hubble flow, they should all be moving away from each other as the sheet expands. Now imagine placing a very heavy bowling ball on the sheet. It creates a deep dimple, a depression in the fabric. Smaller ball bearings nearby will no longer just move apart with the expansion. They will also start to roll downhill into the depression created by the bowling ball. This downhill motion is the peculiar velocity. The Great Attractor is that bowling ball, except it's not a bowling ball. The mass required to create this cosmic depression is estimated to be on the order of 10,000 to 100,000 times the mass of our entire Milky Way galaxy. It is a gravitational well of almost unimaginable depth. Our galaxy and all its neighbours are falling into it. We are cosmic water, spiralling down a drain we cannot see. To pierce the veil of the zone of avoidance, astronomers needed a new kind of eye, one that could see through the dust and glare of the Milky Way. They found it in the different wavelengths of light. Infrared and radio waves, unlike visible light, can penetrate through the galactic dust. They are the keys that can unlock the secrets hidden behind the curtain. Using powerful radio telescopes and infrared surveys, astronomers began to peer into the zone of avoidance, hunting for their quarry. And slowly, a picture began to emerge. They found what they were looking for, a massive cluster of galaxies known as the Norma Cluster, situated right in the heart of the region where the Great Attractor was predicted to be. It was a significant discovery. The Norma Cluster is rich and dense, containing hundreds of large galaxies, and it sits at the intersection of several great cosmic filaments, vast tendrils of dark matter and galaxies that form the cosmic web. It seemed for a moment that the mystery was solved. The Great Attractor was the Norma Cluster. The ghost had a face, but as more data came in, a nagging inconsistency appeared. Scientists began to carefully calculate the mass of the Norma Cluster and its surrounding structures. They counted the galaxies, estimated their stellar mass, and inferred the amount of associated dark matter. The numbers didn't add up. The Norma Cluster and its neighbours were indeed massive, a significant concentration of matter. But they were not massive enough. The observed mass could only account for a fraction, perhaps less than half, of the gravitational pull required to generate the 600 km per second peculiar velocity that we are experiencing. The bowling ball they had found was simply too light to be making such a deep impression on the fabric of space-time. This was a stunning revelation. The Great Attractor was not the Norma Cluster. The Norma Cluster was merely a signpost, a local hotspot of gravity. The true source of the anomaly, the real Titan, lay even further beyond, deeper in the uncharted territory of the cosmos. The detective story had taken a dramatic turn. The main suspect was in custody, but it was clear they had an accomplice, a far larger and more powerful mastermind who was still at large. The search widened. Astronomers pushed their instruments to look even deeper, past the Great Attractor region itself, and there, lying some 650 million light-years from Earth, they found it. A structure so vast, so overwhelmingly massive, that it dwarfed everything else in our local universe. It is called the Shapley supercluster. Named after the pioneering astronomer Harlow Shapley, this is not merely a cluster of galaxies. It is a gargantuan conglomeration of dozens of galaxy clusters, all gravitationally bound into a single, colossal entity. It is the most massive concentration of matter within 1 billion light-years of the Milky Way, a cosmic metropolis containing the mass of over 10 million billion suns. The Shapley supercluster is the true gravitational apex of our cosmic neighbourhood. It is the deep bottom of the well towards which everything is flowing. This discovery fundamentally recontextualised the entire phenomenon. The Great Attractor, the region around the Norma cluster, is not our final destination. It is better understood as a gravitational waypoint. Let us return to our river analogy. Imagine our galaxy as a small raft on a vast cosmic river. For a long time, we thought we were just drifting with the main current of cosmic expansion. Then we noticed we were being pulled sideways towards what seemed like a large whirlpool. This whirlpool is the Great Attractor, but upon closer inspection, we realised this whirlpool isn't the end of the journey. It's merely the beginning of a steep, powerful set of rapids. And these rapids are all flowing inexorably downhill towards a vast, deep, colossal lake. That lake is the Shapley supercluster. Our Milky Way, the Andromeda Galaxy, the Virgo cluster, and the Great Attractor itself are all just different points on this cosmic river, all caught in the irresistible gravitational current flowing towards Shapley. This is where the story moves from a cosmic mystery to a profound challenge, to our model of the universe itself. The existence of a structure as massive as the Shapley supercluster and the enormous bulk flow of galaxies it generates begins to strain one of the most fundamental tenets of modern cosmology, the cosmological principle. This principle is an assumption, a foundational belief, that on the larger scales the universe is homogeneous and isotropic. Homogeneous means it has a roughly uniform density. There are no special places. Isotropic means it looks the same in every direction. There are no special directions. This principle has been incredibly successful. It is the basis for our standard model of cosmology, which so accurately describes the evolution of the universe from the Big Bang to the present day. But the Great Attractor and the Shapley supercluster are not small deviations. They represent an enormous lump in the otherwise smooth cosmic soup. The coherent flow of galaxies towards this region is a giant pointing arrow in a universe that is supposed to have no preferred directions. It raises a deeply unsettling question. Is the universe as uniform as we've always assumed? Or are there structures out there, concentrations of matter and gravity, so large that they break this fundamental symmetry? This isn't just an academic debate. If the cosmological principle is weaker than we thought, it could have cascading effects on our understanding of everything. Our measurements of dark energy, the mysterious force accelerating the expansion of the universe, rely heavily on the assumption of a smooth cosmos. If our local neighbourhood is unusually dense or is experiencing unusual gravitational flows, it could mean our calculations are skewed. The Great Attractor forces us to confront the possibility that we live in a special place, a cosmic province with its own unique gravitational geography, and that our view of the cosmos may be more parochial than we ever imagined. The mystery deepens even further. Some studies have suggested the existence of an even larger, more perplexing motion, dubbed the dark flow. By analysing the motion of the distant galaxy clusters, some astronomers found evidence of a coherent flow on an even grander scale, stretching out for billions of light years. This flow is not directed towards the Shapley supercluster. Its vector points to a region of space far outside our local supercluster complex, towards the constellations of Centaurus and Hydra, but much, much farther away. The implications of the dark flow, if it is confirmed, are staggering. The Shapley supercluster is the largest known mass in our observable universe that could influence us. If there is a flow of matter beyond its grasp, what could possibly be causing it? The proponents of this controversial theory suggest that the culprit may be something from before the Big Bang, or even the gravitational influence of structures that lie outside our observable universe. They propose that our cosmos is being tilted or pulled by other universes in a larger multiverse. This is highly speculative, on the very fringes of theoretical physics, but it demonstrates how the initial puzzle of our peculiar velocity has unravelled into the most profound questions we can ask about the nature of reality. The Great Attractor is not just a place, it is a gateway to the unknown. This saga is also inextricably linked with the two greatest mysteries of modern physics, dark matter and dark energy. The missing mass problem of the Great Attractor is a perfect illustration of dark matter's role. The visible galaxies in the Norma cluster and even the Shapley supercluster do not have enough mass to explain their gravitational influence. The vast majority of the mass pulling us in is invisible. It is dark matter, the mysterious substance that makes up about 85% of the matter in the universe, but which does not interact with light. The Great Attractor is, in essence, a colossal cloud of dark matter, with galaxies sprinkled within it like luminous dust, merely tracing the shape of the true gravitational titan. It is a laboratory for studying the behaviour of dark matter on the largest possible scales. Simultaneously, this entire gravitational drama plays out against the backdrop of a universe being pushed apart by dark energy. Gravity, the force behind the Great Attractor, pulls things together. Dark energy, the intrinsic energy of empty space itself, pushes everything apart. Right now, in our local supercluster, gravity is winning. The pull of Shapley is strong enough to overcome the cosmic expansion, drawing us and our neighbours together into a single cosmic destiny. But on the very largest scales, dark energy is the undisputed victor. The expansion of the universe is accelerating. Galaxies beyond our local supercluster are receding from us at ever-increasing speeds. Eventually, they will cross a cosmic horizon, their light no longer able to reach us. They will vanish from our sky forever. This cosmic competition leads to a poignant and startling vision of the far future. Imagine astronomers billions of years from now. By then, the Milky Way and Andromeda will have merged into a single giant galaxy, Milkomeda. This new galaxy, along with the other members of our local group, will have fallen into the Virgo cluster, and the entire Virgo supercluster will be well on its way to merging with the other structures in the Great Attractor region, all inexorably drawn towards the heart of the Shapley supercluster. The local universe will become a single, massive, isolated supergalaxy. But beyond this cosmic island, the rest of the universe will have disappeared. The relentless push of dark energy will have carried all other galaxies beyond the observable horizon. Future astronomers in this lonely supergalaxy will look out into a sky that is almost completely empty. They will have no evidence of other galaxies, no sign of the Hubble flow, no way of detecting the expansion of the universe. The cosmic microwave background, the echo of the Big Bang, will have redshifted to wavelengths so long as to be virtually undetectable. They might conclude, logically but incorrectly, that they live in a single, static, eternal island universe. The story of our cosmic origins, the evidence for the Big Bang, and the knowledge of the universe's true scale will have been erased by time. Our journey towards the Great Attractor is a fleeting chapter in cosmic history, a clue to the universe's grand structure that is only available for a limited time. We are privileged to live in an era where the evidence is still visible, where the cosmic detective story can still be pieced together. So where does that leave us? We are residents of a galaxy caught in a gravitational river. We are falling at over 1 million miles per hour towards a concentration of mass we can barely perceive. Our ultimate destiny, hundreds of billions of years from now, is to merge with the countless other galaxies being drawn towards the Shapley supercluster, to become part of a single, monumental structure, an island of matter in an ever-expanding sea of nothingness. The Great Attractor does not break the laws of physics. On the contrary, it is a spectacular confirmation of the power of gravity as described by Einstein. But it shatters our sense of cosmic uniformity. It breaks our assumption that the universe is a simple, placid place. It reveals a cosmos that is lumpy, dynamic, and structured in ways that are far more complex and majestic than we ever dreamed. It shows us that even the largest structures we can see may be mere components of even larger systems we're only beginning to glimpse. The Great Attractor is a profound lesson in cosmic humility. It reminds us that our map of the universe is still largely blank, and that in the silent darkness between the galaxies, there are forces and structures of incomprehensible scale that shape our past, our present, and our ultimate cosmic fate. We are not merely observers of the universe. We are participants, travellers on a journey whose destination we are just now starting to comprehend. The pull is undeniable. The journey continues, and the greatest mysteries of space still await us, hiding in the dark. undefined. What if the most magnificent structures in the universe are not the ones we can see? What if the grandest cities of the cosmos are not built from the incandescent fire of 1,000,000,000,000 suns, but from the absolute unrelenting darkness of 1,000,000,000,000 graves? We are taught to look up at the night sky and see a history written in light. Each star is a beacon, a storyteller recounting tales of nuclear fusion, of planetary birth, of the slow majestic waltz of galaxies. The light that reaches your eye tonight began its journey when civilizations on Earth were young, a faint whisper from a distant fiery past. It is a language we have only just begun to understand, yet it has shaped our every conception of the universe. We see galaxies as islands of brilliance, spiraling tapestries of starlight, and glowing gas pinned against the black velvet of infinity. This is our cosmic home, our reference point, the very definition of celestial grandeur. But this vision, this beautiful, reassuring image of a universe filled with light, might only be half the story. It might be the thinnest veneer, a decorative illusion obscuring a much deeper, much stranger, and far more powerful reality. Let us take a journey beyond that veneer. Imagine we could pilot a vessel capable of crossing the unfathomable void between galaxies, a ship that travels not on light, but on the very curvature of space-time itself. We leave behind the familiar glow of the Milky Way, our sprawling home of 400 billion stars becoming a faint receding smear of diamond dust. For millions of years, we travel through an intergalactic desert, a realm of profound emptiness where the silence is so complete it feels like a physical presence. Then our instruments detect something. Not a flicker of light, not a radio wave, not the signature of hydrogen gas coalescing into stellar nurseries. No. Our ship registers something else entirely. It detects a pull. An immense, invisible, and terrifyingly coherent gravitational field, a cosmic undertow dragging us toward an unseen shore. There is a destination ahead, but it is a place of pure blackness. Against the backdrop of the distant universe, there is no silhouette, no shadow, just a subtle, creeping distortion. The light from galaxies, 1,000,000,000 light-years behind our target, begins to bend, to warp, as if seen through a celestial lens of impossible size. This is the first sign that we are approaching a place that breaks all the rules. As we draw closer, the distortion intensifies. The universe behind our destination is smeared into arcs and rings of ethereal, ghostly light, an Einstein ring on a galactic scale. It is a silent cosmic scream, the light of faraway objects being tortured by a gravitational presence of unimaginable mass. Yet as we stare into the heart of this gravitational anomaly, we see nothing. No central bulge of ancient stars, no swirling arms of blue-white giants, no nebulae blushing pink with the energy of newborn suns. There is only the void. We have arrived at a galaxy with no stars, a metropolis constructed exclusively from black holes. You are now crossing the threshold into a kingdom of pure gravity, a civilization of singularities. What does it feel like to be inside the familiar comforts of astrophysics are gone? There is no starlight to warm the hull of our ship, no solar wind to measure. The silence is absolute, a pressure on the soul. But it is not empty. Far from it. This place is teeming with a population of ghosts. All around us in every direction are the invisible inhabitants of this dark galaxy. Stellar mass black holes, the collapsed remnants of stars that might have lived and died in a different, more conventional galaxy long ago, drift like cosmic predators. Each one is a point of perfect darkness, a gravitational pearl weighing several times the mass of our sun, yet compressed into a sphere only a few kilometers across. They are silent, and they are deadly. Get too close, and the tidal forces would shred our ship into a stream of atoms, a final unheard scream into the abyss. We can't see them directly, but we can see their effects. Occasionally a flicker of intense energy erupts in the darkness. A captured rogue planet or a wandering asteroid straying too close to one of these gravitational phantoms is torn apart in a final brilliant flare of radiation. For a brief glorious moment, an accretion disk of superheated matter ignites around the black hole's event horizon, a celestial blowtorch that illuminates the surrounding void before being swallowed forever. These are the only lighthouses in this eternal night, momentary flashes of cataclysm that betray the locations of the unseen monsters that lurk in the dark. And these smaller black holes are merely the common citizens of this impossible metropolis. Deeper within our instruments begin to register even more powerful gravitational sources, entities of a different order of magnitude. These are the intermediate mass black holes, the missing link in cosmic evolution, weighing thousands or even tens of thousands of solar masses. Here in this starless realm they roam as celestial barons, their gravitational reach extending for light years. They are the anchors of their local domains, holding smaller black holes in complex weaving orbits. We witness a silent ballet of gravitational warfare. Two stellar mass black holes locked in an ancient orbital dance spiral ever closer to one another. Their waltz accelerates, they are whipping around a common center at nearly the speed of light, warping the very fabric of spacetime around them. They are not emitting light, but they are screaming in a different language. They are broadcasting gravitational waves, ripples in the cosmos, a symphony of spacetime sung at a frequency we are only just learning to hear. As they merge, a shudder propagates through the universe, a convulsion of pure gravity that carries away a portion of their mass as raw energy. In that single silent instant, more energy is released than by all the stars in all the galaxies of the observable universe combined. And then there is only one larger black hole, and the silence returns deeper than before. This entire structure, this city of silent, invisible titans, is itself in orbit. At the very center of it all, where the core of a normal galaxy would house a supermassive black hole surrounded by a dense cluster of ancient stars, there is only the ultimate sovereign of this dark empire. A true monster, a supermassive black hole of billions of solar masses, a gravitational gyroscope holding the entire starless galaxy in its thrall. We cannot approach it. Even from this distance, its presence is overwhelming a well of spacetime so deep that it dictates the destiny of everything for 1,000,000 light-years in every direction. The other black holes, from the smallest to the largest, are all caught in its majestic, inexorable orbit. They are courtiers circling a dark throne, a royal court of collapsed matter and infinite density. This is a galaxy not of fusion, but of fission and consumption. It doesn't create light, it devours it. It doesn't foster life, it enforces a sterile, perfect order governed by the cold, clean mathematics of general relativity. It is the universe's ultimate feudal system, a hierarchy of gravity from the smallest collapsed star to the incomprehensible singularity at its heart. Now we pull back from this speculative journey, our ship retreating from the edge of this theoretical abyss. The warped light of the background universe straightens out. The pull of the dark galaxy fades. And we must ask the fundamental question that shatters our cosmic perspective: could such a place actually exist? Is this merely a flight of science fiction, a gothic fantasy painted on a cosmic canvas? Or does this chilling, magnificent vision represent a genuine possibility, a new class of object that has been hiding in plain sight, or rather in plain darkness all along? To even consider this possibility requires us to discard our most basic astronomical assumptions. A galaxy, by its very name, derived from the Greek for milky, a direct reference to the appearance of the Milky Way, is defined by its stars. Stars are the engines of galactic evolution. Their light illuminates the gas and dust from which new generations of stars are born. Their stellar winds and supernova explosions enrich the cosmos with heavy elements, the very building blocks of planets and of life itself. A galaxy in our experience is a luminous, dynamic, self-perpetuating system of creation. The object we have just visited is its antithesis. It is a sterile, dark, and seemingly eternal system of gravitational stasis. It is an end state, a cosmic cemetery. To call it a galaxy feels like a contradiction in terms. Yet it possesses the two most fundamental properties of a galaxy: immense gravitationally bound mass and a coherent rotating structure. It has the architecture of a galaxy, the invisible scaffolding, but it is utterly devoid of the luminous population we expect to see. This paradox forces us to confront a profound question. What is the true nature of a galaxy? Is it the stars we see, or is it the gravity we can't? For decades, we have been haunted by a similar puzzle on a much larger scale. We have observed that the galaxies we can see are spinning too fast. the stars on their outer edges are moving with such velocity that the gravity of all the visible matter, all the stars, gas and dust, should be insufficient to hold them in their orbits. By all rights, these galaxies should have flown apart billions of years ago. They have not. There must be something else there, an invisible substance, a source of immense gravity that permeates and surrounds every galaxy, including our own. We call it dark matter. This mysterious component of the universe is the ultimate ghost. It does not emit, absorb, or reflect any light. It interacts with our world, with our very bodies, only through the subtle, persistent pull of gravity. And it is not a minor ingredient in the cosmic recipe. All the stars, planets, asteroids, and shimmering nebulae, everything we have ever seen through a telescope, everything we call matter, accounts for a mere 5% of the universe. The rest is a combination of dark energy, the force driving cosmic expansion, and this enigmatic dark matter which makes up about 27% of the cosmos. For every pound of visible matter, there are more than 5 pounds of this invisible gravitational scaffolding. We are living in a universe that is fundamentally hidden from us. We are the decorative froth on a vast, dark, undiscovered ocean, and for 50 years the greatest minds in physics and cosmology have been locked in a monumental quest to identify this substance. We have built detectors deep underground, shielded from cosmic rays, hoping to catch the fleeting signature of a dark matter particle passing through the Earth. We have smashed protons together in colossal accelerators, hoping to create a particle of dark matter in the laboratory. So far, we have found nothing. The ghost remains elusive. This is where our journey into the starless galaxy transforms from a speculative dream into a radical yet plausible scientific hypothesis. What if dark matter is the key? What if the reason we haven't found a new fundamental particle is because we are looking for the wrong thing entirely? Some theories at the very bleeding edge of cosmology propose that dark matter isn't a particle at all. Instead, they suggest it could be composed of black holes. Not the black holes born from dying stars, but something far more ancient and mysterious. Primordial black holes forged not in the collapse of a star, but in the chaotic, ultra-dense furnace of the Big Bang itself. In the first fractions of a second of the universe's existence, tiny fluctuations in the density of the primordial soup could have been so extreme that pockets of energy collapsed directly into black holes of varying sizes long before the first stars ever had a chance to form. If this theory is correct, the universe could be filled with these ancient invisible relics, a population of primordial singularities that have been shaping cosmic history from the very beginning. Under the right conditions, in a region of the early universe that was exceptionally dense, with these primordial black holes, they could have begun to clump together under their own mutual gravity. While the rest of the cosmos was slowly gathering gas to form the first stars and luminous galaxies, this unique region would have followed a different evolutionary path. It would have bypassed the age of starlight entirely. It would have skipped the entire process of stellar evolution, proceeding directly to a final, gravitationally dominated state. It would have become a dark galaxy, a structure composed not of matter that failed to shine, but of objects that were born dark and have remained so for 13 billion years. The existence of even one such galaxy would be a smoking gun. It would be the single greatest cosmological discovery in history, a profound and revolutionary confirmation of our theories about the universe's first moments. It would solve the puzzle of dark matter overnight, transforming it from a theoretical placeholder into a tangible, if terrifying, population of real objects. Finding it, however, is a monumental challenge. How do you find a galaxy that is by its very nature invisible? You cannot search for it with conventional telescopes that look for light. You must search for its gravitational shadow. We would have to survey the entire sky not for points of light, but for regions where the light from everything behind it is systematically and coherently warped. We would need to search for colossal gravitational lenses that have no visible galaxy at their centre. It is an observational quest of breathtaking audacity, pushing the limits of our technology and our ingenuity, but the reward would be immeasurable. It would be like discovering a new continent on Earth, but this continent would be woven into the very fabric of reality, its shores defined by the curvature of space-time. It would mean that the universe we see is only a pale imitation of the one that truly exists. It would prove that the dominant form of structure in the cosmos is not the luminous, vibrant spiral of a Milky Way, but the cold, dark, and silent majesty of a galaxy of black holes. This is the story we are about to embark on, a search for a monster in the dark, a quest to understand the invisible architecture of our universe and to solve the most profound mystery in all of science. We will journey back to the dawn of time, to the fiery crucible of the Big Bang, to understand how such an object could possibly form. We will explore the bizarre physics of its interior, a place where time and space are stretched to their breaking points. And we will join the hunt, following the astronomers who are pioneering new ways to see the unseeable, sifting through mountains of data for the telltale gravitational signature of a starless ghost. The stakes could not be higher. The answer will not only redefine what a galaxy can be, it will redefine our place within the cosmos. It will tell us whether we live in a universe dominated by light and life, or whether we are just a fleeting luminous accident in a universe that belongs ultimately to the dark. The journey begins now as we step past the veil of starlight and into the shadowlands of the cosmos. Is it possible to build a galaxy without a single star? Could you assemble a sprawling city-sized structure in the cosmos, a gravitational empire 100,000 light-years across that is utterly, eternally and completely dark? It's a question that seems to violate the very definition of what we see when we aim our most powerful telescopes into the deep. For millennia, our story of the universe has been a story of light. We have charted our existence by the steady glow of distant suns and measured the vastness of space by the cities of light they form. These are the galaxies, the fundamental architecture of the cosmos. They are lighthouses in the cosmic ocean, each one a testament to the universe's profound, unquenchable thirst to create light. Take our own home, the Milky Way, as a blueprint for creation. It is a spinning disk of such impossible scale that light itself, the fastest thing in existence, takes 100 millennia to cross it. Within its spiraling arms, we estimate there are 400 billion stars, an incandescent population of stunning diversity and violence. There are colossal blue giants, celestial blowtorches burning through their fuel in a brilliant flash of cosmic youth, destined to die in spectacular explosions. There are suns like our own, stable and yellow, patiently warming their worlds for billions of years, providing the essential energy for life's great experiment. And there are the ancient crimson embers of red dwarfs, tiny stubborn stars that will sip their hydrogen for trillions of years, hoarding their light, long after the rest of the galaxy has gone dim. These stars are the engines of cosmic alchemy. Forged in their nuclear hearts are the elements of which we are made, the carbon in our cells, the oxygen we breathe, the iron in our blood. When they die, they seed the cosmos with these precious materials, enriching the great clouds of gas and dust that drift between them. This interstellar medium, this ethereal fog of hydrogen and helium laced with the fine dark soot of exploded suns, is the galaxy's soul. It is both a graveyard and a nursery. Here in vast cold molecular clouds, gravity begins its patient work, gently pulling filaments of gas together, denser and denser, until new stellar cores ignite and the cycle of light begins anew. We see these nurseries as glowing nebulae, painterly splashes of pink and blue, where the fierce radiation from newborn stars illuminates the surrounding gas, creating some of the most beautiful vistas the universe has to offer. A galaxy, then, is not a static object, but a living, breathing ecosystem. It is a dynamic interplay of matter and energy, a churning cauldron where stars are born live and die, constantly recycling the stuff of creation. This luminous matter, the stars, the gas, the dust, is what we see. It is what we have always called the galaxy. And for most of the 20th century we believed it was all there was. We thought that if we could count up all the light, we could account for all the matter. We were about to discover how profoundly, terrifyingly wrong we were. The first hint of a deeper hidden reality came not with a bang, but a graph. In the 1970s, an astronomer named Vera Rubin was doing something revolutionary, something that many of her colleagues considered tedious and unglamorous. She was meticulously measuring the speed of stars within distant galaxies. The prevailing logic was simple, a direct echo of our own solar system. Planets closer to the Sun move faster than those farther out where the Sun's gravitational grip is weaker. Mercury zips around in 88 days. Neptune takes a century and a half. Galaxies everyone assumed should behave in precisely the same way. Stars near the bright, dense galactic centre should be moving at incredible speeds, while stars on the far, lonely outskirts should be moving much more slowly, their orbits dictated by the visible mass of the galaxy they circled. But that is not what Vera Rubin found. Her data gathered over countless nights at the observatory revealed something impossible, something that defied the laws of physics as we knew them. The stars on the outer edges of the galaxies she studied were moving too fast. In fact, they were moving just as fast as the stars much farther in. It was the gravitational equivalent of finding that Neptune orbits the Sun at the very same speed as Mercury. The implications were staggering and deeply unsettling. For these outlying stars to be moving so quickly without being flung off into the blackness of intergalactic space like stones from a slingshot, there had to be an enormous amount of extra gravity holding them in place. There had to be a colossal sphere of invisible mass extending far beyond the visible edge of the starlight, a gravitational anchor holding the entire spinning city together. When Rubin and her colleagues calculated how much mass was needed, the answer was not a minor correction. It was a paradigm-shattering revelation. The visible galaxy, the glorious spectacle of 400 billion stars, the glowing nebulae and the dark lanes of dust, accounted for a mere 15% of the total mass. 85% of the universe, it seemed, was missing. Or rather, it was not missing. It was hiding. It was there all around the galaxies, enveloping them in a vast unseen halo, a substance that did not shine or burn or reflect or block light in any way, a form of matter that was utterly profoundly dark. This discovery of what we now call dark matter was a moment of profound humility. It was the cosmic equivalent of exploring a city at night for centuries, mapping its streetlights and neon signs with exquisite precision, only to have the sun rise and reveal the enormous invisible mountains and continents upon which the city was built. Everything we had ever observed from the dawn of humanity until that moment was just the foam on the surface of a vast invisible ocean. The challenge was immense. How do you prove the existence of something that by its very nature is defined by its refusal to be seen? You cannot point a telescope at it. You cannot collect a sample of it. You can only infer its presence by the way its immense gravity warps the space-time and light that passes through it. You hunt for the ghost, not by seeing it, but by watching the curtains move. One of the most powerful tools in this ghost hunt is an effect predicted by Einstein's theory of general relativity gravitational lensing. Einstein revealed that massive objects don't just sit in space-time. They bend it, creating curves and divots like a heavy ball on a rubber sheet. Light, which always travels in a straight line, must follow these curves. So if a massive object like a galaxy cluster sits between us and a more distant source of light, the space-time it warps acts like a lens, a cosmic telescope that magnifies, distorts, and even creates multiple images of the background object. When astronomers observe massive galaxy clusters, the lensing effect they see is far, far stronger than what could be produced by the visible galaxies alone. The light from background objects is smeared into impossible arcs and ghostly rings, a celestial funhouse mirror whose distortions betray the presence of an immense, smoothly distributed halo of invisible matter. We can use the precise nature of these distortions to reverse engineer a map of the ghost's gravitational field and therefore its mass. And every time we do, the map reveals the same thing. The visible matter is just a small glittering jewel set within a vast invisible crown of dark matter. Perhaps the most compelling piece of evidence comes from an object known as the Bullet Cluster, a truly extraordinary cosmic crime scene. Here we see two galaxy clusters that have passed directly through one another in a collision of unimaginable scale and violence. During this cataclysm, the normal matter, the vast clouds of hot gas crashed together, slowed down, and now glows intensely in X-ray light, forming a shockwave near the centre of the wreckage. But the dark matter, which does not interact with anything except gravity, behaved very differently. The vast halos of dark matter from each cluster seem to have passed straight through each other like ghosts, continuing on their original paths, completely unfazed by the collision of normal matter. Using gravitational lensing, we can map the location of the mass in the system, and we find that most of the mass is not where the glowing gas is. Instead, it is located in two distinct clumps on either side of the collision, perfectly co-located with the galaxies where the dark matter should be. The bullet cluster gives us a clear, unambiguous separation of normal matter from dark matter. It is the universe's smoking gun. The ghost has been caught on camera, its silhouette outlined by warped starlight. The evidence is now overwhelming, drawn not just from spinning galaxies and distorted light, but from the very cradle of the universe itself. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we are seeing a baby picture of the cosmos taken when it was just 380,000 years old. This ancient light is not perfectly uniform. It is mottled with tiny fluctuations in temperature-minute hot and cold spots that represent seeds of density. These were the seeds that would over billions of years grow into the vast structures of galaxies and galaxy clusters we see today. But our supercomputer simulations, which can model the evolution of the universe with breathtaking accuracy, deliver a stunning verdict. If the universe had only contained the normal baryonic matter, we know there simply would not have been enough time for gravity to pull that matter together to form the galaxies we inhabit. The initial fluctuations were too small, the expansion of the universe was too fast. The simulations only work, they only produce a universe that looks like our own if there was a pre-existing invisible scaffolding of dark matter. This dark matter, 5 times more abundant than normal matter, began clumping together long before the first atoms even formed. It created deep, gravitational wells, cosmic potholes into which normal matter could later fall, accelerating the process of galaxy formation. Without dark matter, there would be no Milky Way, there would be no Sun, there would be no Earth. We owe our very existence to a substance we have never seen and do not understand. This realization has launched one of the greatest scientific quests in human history, the hunt for the dark matter particle. For decades, the leading suspect was a class of hypothetical particles known as WIMPs, or weakly interacting massive particles. The theory was elegant. WIMPs would have been produced in vast numbers in the hot dense soup of the early universe. They would be heavy, slow-moving, and as their name suggests, they would only interact with normal matter through gravity, and the weak nuclear force making them nearly impossible to detect. Physicists have built breathtakingly sensitive experiments to search for them. Deep underground in mines and tunnels shielded by kilometers of solid rock from the constant rain of cosmic rays, scientists have built vats of supercooled liquid xenon, or arrays of pristine germanium crystals. The hope is that just once in a great while a WIMP from the galaxy's halo drifting through the Earth, through the rock, through the experiment itself, might score a direct hit on an atomic nucleus, producing a minuscule flash of light or vibration, a whisper of its passage. Billions of dollars and decades of searching have passed. The experiments have grown ever more sensitive, ruling out vast swathes of possibilities. And yet they have found nothing, only a profound, deafening silence. The persistent lack of a signal has pushed physicists to consider other, even more exotic possibilities. Perhaps dark matter is not a WIMP but an axion. These are hypothetical particles that are almost unimaginably lightweight, billions of times less massive than an electron and even more ghostly. They are less like individual particles and more like a vast coherent wave sloshing gently throughout the galaxy. Detecting them requires a completely different strategy, using incredibly powerful magnetic fields to try and coax an axion to transform into a single, detectable photon of light. The search is on, but the challenge is monumental. We are searching for a ghost, and our best efforts have so far only deepened the mystery, leaving us to wonder if we're even looking for the right kind of ghost. What if the answer isn't a new exotic particle from beyond our current theories? What if dark matter isn't a feebly interacting something, but a powerfully interacting nothing? What if the solution has been lurking in our cosmic backyard all along? A conclusion so simple, so dark, and so terrifyingly familiar that we have been reluctant to fully embrace it. Let us consider a truly radical idea. What if dark matter is made of black holes? not the kind of black holes we know best, the stellar mass behemoths left behind when giant stars exhaust their fuel and collapse under their own weight. Those are made of normal baryonic matter and we can account for them. Instead, we're talking about something much older, much stranger. Primordial black holes, or PBHs. These are not the children of dying stars, they are children of the Big Bang itself. In the very first second of the universe's existence, the cosmos was a place of unimaginable density and violent fluctuation. It is theoretically possible that in some regions the primordial plasma was so incredibly dense that it spontaneously collapsed under its own gravity, directly forming black holes without ever having been a star. These primordial black holes could have formed with a vast range of masses from the weight of an asteroid to thousands of times the mass of our Sun. And once formed, they would be fantastically stable, persisting for eons. They would be the perfect dark matter candidate. They are made of the same protons and neutrons as us, but they were locked away inside an event horizon before the era of cosmic nucleosynthesis, the process that forged the light elements in the early universe. This means they neatly sidestep the strict cosmological limits on how much normal baryonic matter can exist. They are compact, they are massive, and they interact with their surroundings almost exclusively through the force of gravity. They are for all intents and purposes dark. For many years, the PBH hypothesis was considered a fringe outlandish idea. Astronomers have conducted painstaking surveys searching for microlensing events, where a compact dark object passing in front of a distant star would briefly magnify its light, betraying its presence. These surveys have successfully ruled out PBHs in certain mass ranges. If dark matter were made of primordial black holes the mass of our Moon or Jupiter, or even our Sun, we should have seen them by now, and we haven't. Furthermore, very small primordial black holes, those less massive than a mountain, would have evaporated by now through a process known as Hawking radiation, their departure marked by a final flash of gamma rays we have not detected. But in this cosmic game of hide and seek, a few tantalizing windows remain open. There are specific mass ranges, one around the mass of a large asteroid and another between 10 and 100 times the mass of the Sun, that are not yet ruled out by our observations. And in recent years, a stunning new clue has emerged from the darkness. Gravitational wave observatories like LIGO and Virgo have begun to hear the universe detecting the faint chirps of spacetime ripples from colliding black holes. Some of the black holes they have detected are in a curious mass range around 30 to 50 solar masses, larger than what is easily explained by the collapse of a single star in our modern universe. Could these be the echoes of primordial black holes finally colliding after 13 billion years of silently orbiting one another in the dark? The question hangs in the air, a thrilling and disquieting possibility. We have built our understanding of the cosmos on a foundation of light. But what if the universe's dominant architecture is built from its opposite? If dark matter is indeed a sea of primordial black holes, it forces us to ask a far more profound and unsettling question. Could you take this concept to its ultimate conclusion? Could gravity in the absence of light sculpt these ancient objects into a structure that mimics everything we know about a galaxy? Could you build an entire galactic empire populated not by stars, but by 1 trillion silent, unseen black holes, a city of pure gravity held together by the darkness that birthed it? A galaxy with no stars, a galaxy of ghosts. To forge such a galaxy, a ghost realm of pure gravity, we need more than just a few collapsed stars born in the comfortable adolescence of the universe. We need a legion of black holes, an unimaginable swarm, and for that we must journey back beyond the first stars, beyond the first atoms, back to the overture of existence itself, to a moment of such violence and creation that our minds can barely grasp its fury. We must return to the forge, to the first fractions of the first second where the rules of reality were still being written, and where the universe was not a place of cold, empty space, but a cauldron of pure, seething energy. In this primordial state, less than a second after the Big Bang, there was no up or down, no here or there in any sense we would recognize. There was only a superheated, terrifyingly dense plasma, an incandescent soup of fundamental particles screaming into being. The entire observable universe with its trillions of galaxies was compressed into a volume smaller than a single grain of sand. The pressure was infinite. The temperature was beyond all reckoning. It was here in this cosmic pressure cooker that the seeds of our starless galaxy might have been sown. Not from death, but from the very act of birth, to understand how you must discard the idea of a perfectly smooth and uniform beginning. On the larger scales, the early universe was astonishingly consistent, a near-perfect homogeneity that has puzzled cosmologists for decades. But if you could have zoomed in down to the impossibly small realm of the quantum, you would have seen a different picture. You would have witnessed a universe trembling with uncertainty. The fabric of space-time itself was a roiling, frothing sea of energy, spontaneously bubbling with quantum fluctuations. Tiny, fleeting variations in density and energy that would appear from nothing exist for an immeasurable instant and vanish again. These were not just minor imperfections, they were the genetic code of the cosmos. In a stable, placid universe, these fluctuations would have remained insignificant, a microscopic tremor on the face of creation. But the infant universe was anything but stable. It was about to undergo the single most dramatic expansion in its entire history, an event known as cosmic inflation. In a sliver of time so small it beggars belief, a trillionth of a trillionth of a trillionth of a second, the universe swelled exponentially. It wasn't an explosion in space. It was an explosion of space itself. A moment of divine acceleration that stretched the cosmos from subatomic to macroscopic. This incredible act of cosmic inflation acted like a celestial amplifier. It took those minuscule, ghostly quantum fluctuations and magnified them, stretching them across vast cosmic distances. A ripple that was once smaller than a proton was suddenly larger than a solar system. The universe in its explosive growth had made its own quantum jitters permanent, freezing them into the expanding fabric of space-time as genuine large-scale variations in density. Most of these density perturbations were subtle, representing regions just a fraction of a percent denser than their surroundings. These were the blessed patches, the fertile grounds where hundreds of millions of years later, gravity would gently gather gas to ignite the first stars and sculpt the first galaxies. They are the reason we exist. But what if some of these fluctuations were not so gentle? What if in that chaotic quantum foam, a few initial tremors were exceptionally violent? What if inflation stretched one of these over-dense ripples to a critical breaking point? In that turbulent plasma you would have a pocket of matter and energy so profoundly, so overwhelmingly dense, that the universe's own immense outward pressure could not save it. Here in the searing heat of the first second, the force of gravity, usually the weakest in the cosmos, would become an indomitable tyrant. With no star to collapse, no nuclear fusion to fight back, this lump of primordial energy would succumb to its own immense gravitational pull. It would collapse in on itself catastrophically and completely. The result is not a star, not a planet, not any form of matter we know. The result is a knot tied in the fabric of space-time itself. A primordial black hole, born not from the ashes of a dead sun, but forged directly from the raw, untamed energy of the Big Bang. These are the ghosts we are hunting, phantoms born before the first light ever shone, carrying within them the secrets of the universe's first moments. Unlike their stellar mass cousins, which are constrained by the size of the stars that create them, these primordial black holes could theoretically have formed with a vast spectrum of masses. Some could be as light as an asteroid, others as massive as 1,000 suns, all depending on the precise power of that initial quantum ripple. Here then is the theoretical foundation for our galaxy of darkness, a mechanism born from the union of quantum mechanics and general relativity that could have flooded the early cosmos with a plague of invisible monsters. It's a breathtakingly elegant solution. It suggests that black holes are not cosmic aberrations, but a fundamental, even necessary byproduct of creation. Perhaps the universe was always destined to be haunted, populated from its very first breath by these gravitational phantoms. They would be the ultimate form of dark matter, the missing mass that astronomers have been searching for, silently shaping the galaxies we see, while remaining completely invisible to our telescopes. Our ghost galaxy, once a fever dream, suddenly seems plausible. A structure built from these ancient relics, a city of the dead that has existed since the dawn of time. It's a compelling narrative, a story that seems to fit. But science is not a storyteller, it is a detective. And when we turn from the elegant purity of theory to the messy, demanding world of observation, the case for a universe dominated by primordial black holes begins to encounter serious formidable challenges. The cosmos, it seems, is exceptionally good at hiding its secrets, but it is not perfect. It leaves behind fingerprints clues for those who know how to look. The first major hurdle comes from one of the most exotic predictions of physics Hawking radiation, the idea that black holes are not entirely black, but instead slowly, painstakingly evaporate over immense timescales by leaking particles into the void. This cosmic sizzle is incredibly faint for large black holes, taking longer than the current age of the universe for a solar mass black hole to lose any significant energy. But for smaller primordial black holes, the effect is catastrophic. Any primordial black hole born with a mass less than a large mountain would have already evaporated completely by now, ending its long life in a final brilliant flash of gamma rays. Astronomers have scoured the skies for this telltale signal, this final ghostly sigh from the dawn of time. They have found nothing. No chorus of evaporating black holes, no inexplicable bursts of high-energy radiation. This powerful absence places a hard limit on our theory. The smallest of our proposed building blocks for the dark galaxy simply cannot exist today. They have all vanished. This erases a huge portion of the possible candidates, forcing us to look at only larger, more stable primordial black holes. But as we move up in mass, we encounter a new problem, one of gravitational distortion. If our own Milky Way halo were filled with, say, moon-mass to Earth-mass primordial black holes, they would constantly be drifting between us and the distant stars we observe. Einstein's theory of relativity tells us that their gravity should bend the light of those background stars, acting like cosmic magnifying glasses. This effect, known as gravitational microlensing, should make a star briefly and characteristically brighten as a black hole passes in front of it. For years, dedicated surveys have stared relentlessly at millions of stars, patiently waiting for these fleeting flickers of light. They have found some, but they have not found nearly enough. The number of observed microlensing events is orders of magnitude lower than what we would expect if all of the galaxy's dark matter were composed of these compact objects. The verdict from these meticulous observations is stark primordial black holes in this specific mass range from the mass of the Moon up to 100 times the mass of the Sun cannot be the dominant component of dark matter. The sky is simply too quiet, too stable. The gravitational lenses are missing. We are being cornered. The very small ones evaporated. The medium-sized ones are ruled out by microlensing. So what about the truly massive ones, primordial black holes born with hundreds or even thousands of solar masses? Surely these titans would be too rare to be caught by microlensing surveys. Here we face yet another observational wall, this time built from the oldest light in the universe, the cosmic microwave background. This faint pervasive afterglow of the Big Bang is a snapshot of the universe when it was just 380,000 years old. It is an image of pristine, almost perfect uniformity. If a significant population of massive primordial black holes had existed back then, they would have been cosmic wrecking balls tearing through the primordial plasma. Their immense gravity would have dragged in surrounding matter, creating superheated accretion disks that would blaze with X-rays and other forms of high-energy radiation. This inferno of activity would have injected enormous amounts of energy into the young universe, distorting that pristine snapshot of the cosmic microwave background in ways that would be unmistakable to our modern instruments. Furthermore, this process of accretion would continue through cosmic history. These wandering giants would heat up gas in dwarf galaxies and disturb the delicate orbits of stars in ancient globular clusters. We have searched for these signatures. The Planck satellite mapped the ancient light with unprecedented precision. We have studied the temperature of intergalactic gas and the dynamical stability of the oldest star systems. Again and again, the universe gives us the same answer: silence. We see no evidence of this widespread heating. We find no sign of the gravitational disruption that should be there. The constraints are tight like a closing fist. Every observation we make, every piece of data we collect seems to add another lock to the door, making it harder and harder for a vast population of primordial black holes to exist. So we find ourselves at a profound and deeply unsettling impasse. The theory is beautiful, born from the most fundamental physics we know. The idea of a ghost galaxy built from the universe's firstborn objects is poetically irresistible, and yet the evidence seems to scream that it is impossible. The universe appears to have been swept clean. The smallest have died out, the medium are not seen, and the largest should have left scars on creation that we simply do not find. The grand hypothesis that primordial black holes are the sole solution to the dark matter mystery, and thus the material for our starless galaxy, appears to be crumbling under the weight of observational fact. Is this the end of our journey? Is the starless galaxy just a figment of our imagination, a fascinating but ultimately failed idea? The case seems bleak. We have a motive and a murder weapon, a theoretical origin for these phantoms, but no bodies. And all the available forensic evidence suggests the crime never even took place. The detective work of astrophysics points to an empty room, a silent cosmos devoid of the ghosts we are so desperate to find. It feels like a definitive final answer, a cosmic dead end. But the universe is rarely so simple, and the story of science is not one of open and shut cases, but of mysteries that deepen with every new clue. While the evidence rules out primordial black holes being all of the dark matter in most scenarios, it has not ruled them out completely. Within these vast restrictive walls of evidence there remain intriguing windows of possibility, narrow corridors of mass and abundance, where these elusive creatures might still be hiding. Perhaps they are not the all-encompassing solution we imagined. Perhaps they are something more subtle, more complex. And perhaps our methods for searching have been looking in the wrong places for the wrong kind of ghost. The case is not closed. It has just become infinitely more challenging, and in doing so, infinitely more interesting. We are not looking for a simple answer anymore. We are looking for a loophole in the laws of nature. And so, for generations, the very notion was relegated to the fringes, a ghost story told by cosmologists around a dying fire. It was a mathematical curiosity, an elegant but empty equation. A galaxy of black holes without a single star to light its abyssal corridors seemed like a fundamental violation of cosmic reason. A tree without leaves, a heart without blood. After all, we had always believed that gravity needed a seed, a kernel of ordinary matter around which it could gather the darkness. Galaxies in our grand and unfolding story were built by stars. They were the architects, the engineers, the engines of creation, and dark matter was simply the scaffolding upon which their luminous cities were constructed. The idea that you could have the scaffolding without the city, that the darkness itself could coalesce into a self-sustaining metropolis of pure gravity, felt less like science and more like a fever dream. It was a concept so profoundly alien that it lingered only in the footnotes of obscure papers, a testament to the boundless imagination of theorists, but not a serious contender for reality. For an object to exist in our universe, we reasoned it had to participate. It had to announce itself with light, with energy, with some form of interaction beyond the cold, indifferent pull of its own mass. A silent, invisible galaxy was a contradiction in terms and ontological paradox. It was an object defined only by its absence, and science, for the most part, is the study of what is present. The evidence was all around us. Wherever we found a great concentration of mass, we found light. We saw the brilliant blaze of quasars, the sprawling arms of spirals, the gentle glow of elliptical cities of suns. The universe screamed its existence at us across a symphony of wavelengths. To suggest that an equal, perhaps greater creation could exist in perfect eternal silence was to challenge the very grammar of the cosmos we thought we understood. The consensus was firm, a bulwark of established theory, against which such waves of speculation would inevitably break and dissipate. Our models were clear, our observations consistent. The universe, while mysterious, was not thought to be duplicitous. But even the most formidable walls of scientific consensus are not built on solid bedrock. They are built on the shifting sands of observation and theory, and sometimes tremors from the deepest foundations of physics can create cracks. And through those cracks the most outlandish ideas can begin to seep. For us, the tremors began not with a bang, but with a whisper, a persistent nagging anomaly in our understanding of the universe's very first moments. The standard story of creation. The Big Bang was one of almost impossible smoothness. The cosmic microwave background radiation. The afterglow of that first fire shows us a universe that was astonishingly uniform, with temperature variations of only 1 part in 100,000. From this near-perfect homogeneity, gravity had to slowly, painstakingly gather matter together over hundreds of millions of years to build the first stars and galaxies. It was a slow, bottom-up process, a patient construction project on a cosmic scale. This model, elegant and powerful, explained so much of what we see. But it also had its own ghosts, its own dark corners where the numbers didn't quite add up. It struggled to explain the supermassive black holes we see in the hearts of galaxies today, which appear far too large to have grown so quickly in the early universe. It left the true identity of dark matter as a profound, unanswered question. The story was good, but we were beginning to realize it might not be the whole story. Perhaps the dawn of time wasn't so gentle. Perhaps the cosmic nursery was a far more violent and chaotic place than we had ever dared to imagine. The turning point came from a bold re-examination of the inflationary epoch, that hyper-accelerated expansion of space in the first trillionth of a second. New models began to suggest that this process wasn't the perfectly smooth inflation we had long envisioned. Instead, some theorists proposed a scenario known as lumpy inflation. Imagine the energy field driving this expansion not as a placid lake, but as a boiling, churning cauldron of unimaginable power. In this cauldron, quantum fluctuations would be magnified to astronomical scales. Some regions of space would inflate smoothly, becoming the vast, relatively empty voids we see today. But other smaller pockets could hit a sort of cosmic snag. In these regions, the inflationary energy might linger for a fraction of a second longer, dumping a colossal amount of density into a space smaller than an atom. The pressure and density in these pockets would be so extreme that they would overwhelm every other force in nature. They would collapse instantly under their own impossible weight directly into black holes. They wouldn't need a dying star. They wouldn't need a slow process of accretion. They would be born directly from the raw, untamed energy of the Big Bang itself. These were the primordial black holes the PBHs forged not in stellar death, but in cosmic birth. This new theory did something revolutionary. It provided a natural mechanism for creating a vast population of black holes before the first star had even been conceived. And crucially, it predicted that their formation wouldn't be uniform, it would be biased. In the regions of the cosmic web where the initial density of matter was destined to be highest, the very places where dark matter halos would eventually form this process of spontaneous collapse would have been far more efficient. It was a stunning revelation. The theory suggested that the seeds of dark matter halos weren't just seeded with some mysterious ethereal particle. They could have been seeded with a plague of black holes. The framework of the universe, that great cosmic web of filaments and nodes, could have been built not from ghostly scattered particles, but from these concrete massive gravitational anchors forged in the first inferno. The dark scaffolding wasn't just a placeholder for the luminous city to come. The scaffolding in these select regions could have been the city itself, a pre-built metropolis of darkness, waiting for a history that would never arrive. This was no longer pure speculation. It was a theoretical consequence of a plausible new cosmology. It offered a breathtakingly direct solution to the dark matter mystery, suggesting it wasn't a new particle we needed to find, but a very old, very familiar monster we had simply failed to recognize in sufficient numbers. The universe might not have needed to invent a new substance to account for its missing mass. It might have just used the most efficient storage method for mass and energy it had ever devised, the black hole. For years, this remained a brilliant but untestable idea. A compelling story, but one without a single shred of physical proof. We had a powerful motive and a credible suspect, but the crime scene in the early universe was billions of years old, its evidence shrouded in the mists of time. How could you possibly find proof for a population of invisible objects that have done nothing but orbit one another in the dark for 13 billion years? The answer, it turned out, was not to look for them, but to listen for the sound of their collisions, an echo of violence propagating not through the air but through the very structure of space-time. When the laser interferometer, gravitational wave observatory LIGO, first opened its exquisitely sensitive ears to the cosmos in 2015, it was expecting to hear a certain kind of sound. The gentle chirps of merging neutron stars or the predictable crescendo of black holes, born from the collapse of massive stars. And it did hear those things, but it also heard something else. It heard monsters in the dark. The detectors registered mergers of black holes with masses of 30, 40, even 50 times that of our Sun. This was a profound shock to the system. According to our best models of stellar evolution, it should be incredibly difficult, if not impossible, to form black holes in this specific upper mass gap. A star massive enough to theoretically produce such a large black hole would in its final moments likely undergo a process called a pair instability supernova, a cataclysmic explosion so violent that it would blow the star completely apart, leaving nothing behind. No black hole, no remnant, just an expanding cloud of enriched gas. Yet here was the evidence written in the language of trembling spacetime. These black holes existed. They were real, and they were colliding all over the universe. Where were they coming from? The mystery deepened with every new detection. The gravitational wave observatories became cosmic forensic labs, and the data they collected painted a perplexing picture. The fingerprints of these merging black holes, their masses and their spins, didn't quite match the profile of our usual suspects. Stellar-born black holes formed in the turbulent environments of star clusters should often be spinning rapidly, tilted at odd angles from their orbital dance, reflecting the chaotic history of their lives. But many of these strange new mergers seemed too clean. Their spins were often low or neatly aligned, suggesting they had been born together or had spent eons in a placid, isolated environment, slowly circling one another in a predictable, undisturbed waltz. It was the signature of an old quiet population, not one forged in the heart of a blazing galactic forge. And then there was the question of location. While many mergers could be traced back to the general vicinity of known galaxies, a baffling number of them seemed to be happening out in the cosmic wilderness, in the vast empty voids between the great galactic superclusters. This was deeply troubling. It was like finding evidence of a massive naval battle in the middle of a desert. Black holes, as we understood them, should be where the stars are. They are the children of stars, the grandchildren of galaxies. To find them merging in the lonelier stretches of the cosmos, far from any conceivable parent galaxy, was a flagrant violation of astrophysical etiquette. It hinted at a vast hidden population of black holes, a diaspora unbeholden to the lighted structures of the universe. A population that didn't need stars or gas or galaxies to exist. A population that was itself the destination. This is where the two revolutionary streams of thought, the theoretical possibility of primordial black holes and the observational puzzle of gravitational waves, began to converge, carving a powerful new channel in the landscape of cosmology. What if the strange mergers LIGO was detecting were not from stellar graveyards at all? What if they were the first audible signals from that ancient hidden population of PBHs? It explained everything with an astonishing elegance. Their forbidden masses were no longer forbidden, because they were never subject to the limits of stellar evolution. Their low-aligned spins made perfect sense if they were formed as primordial pairs in the early universe, bound together by gravity from the very beginning. And their lonely locations in the cosmic voids were no longer a mystery if they were the inhabitants of their own invisible structures, their own dark galaxies drifting silently through the intergalactic medium. The whispers from the dawn of time and the echoes in space-time were telling us the same story. A new grander vision of cosmic structure began to emerge from the synthesis. We had always pictured a dark matter halo as a diffuse spherical cloud of tiny weakly interacting particles surrounding a visible galaxy like a ghostly fog. But what if this picture was completely wrong? What if a halo wasn't a fog but a swarm? A self-gravitating dynamic and evolving system composed not of trillions of microscopic particles, but of millions, or perhaps billions of macroscopic black holes. This was the birth of the dark galaxy concept as a tangible physical entity. It would not be a halo in the traditional sense, but a true galaxy in its own right, obeying all the same laws of gravity and motion as our own Milky Way. The primordial black holes would act as its stars, each one orbiting a common barycenter, the silent, unseen heart of the structure. It would have a gravitational potential, well, a core, a disk, perhaps even globular clusters made of smaller black holes orbiting in its periphery. It would be a living, breathing system, just one that operated on principles of pure gravity, stripped of all the messy, complicated physics of gas dynamics, radiation, and star formation. It would be a celestial machine of perfect efficiency and terrifying simplicity. Its evolution would be a slow, majestic dance of gravitational encounters. Over billions of years, some black holes would be flung out into intergalactic space through three-body interactions, becoming cosmic wanderers. Others would sink toward the core, their orbits decaying until they met in that final violent chirp that our detectors on Earth could overhear. These dark galaxies would be the ultimate cosmic predators, moving through the universe as gravitational ghosts. They would be utterly invisible to every telescope we had ever built, blind to every wavelength of a light. And yet their presence would be undeniable. They would bend and warp the light of more distant objects. They would gravitationally shepherd and perturb the small dwarf galaxies that strayed too close. They would be the dark puppeteers of the cosmos, their strings made of pure space-time curvature. Imagine for a moment journeying through such a place. Your ship's sensors would register nothing. No radio signals, no infrared heat, no ultraviolet radiation. Only blackness. A perfect, featureless void that would feel more empty than the deepest intergalactic space. Yet your navigation systems would be screaming, fighting against a powerful and complex gravitational field. You are not in empty space. You are flying through the heart of a city of 1 billion suns, each one collapsed to an infinitesimal point. There is structure here. There are gravitational tides, currents, and eddies. As you pass close to one of its stars, a black hole 12 times the mass of our sun, you would feel the immense tidal forces trying to tear your ship apart. But you would see absolutely nothing. There is no accretion disk, no fiery ring of matter, because there is no matter to accrete. It is a clean black hole, a perfect sphere of warped space-time against a black background. The only light you might ever see would be the brief, terrible flash of a merger, a silent, instantaneous eruption of gravitational waves, and a flicker of high-energy photons from the disturbed vacuum itself, a spark of momentary violence in an eternity of calm. This is not just a collection of objects, it is a coherent entity. A gravitational gyroscope spinning in the dark its immense collective angular momentum, providing a stability that could persist for trillions of years. It is a cosmic anchor, a reservoir of mass so dense and so dark that it forms the bedrock upon which the lighted universe is built. This powerful, terrifying, and beautiful idea transformed the black hole galaxy from a philosophical curiosity into a concrete physical prediction. It was no longer a ghost story. It was now a target, a testable hypothesis. The question was no longer, could such a thing exist, but had become, how do we find it? We could not search for its light because it has none. We cannot search for its shadow because it is cast against a background of utter blackness. We have to search for the one thing it cannot hide: its gravity. The immense collective gravity of 1 billion black holes gathered in one place would act as a colossal gravitational lens, but it would be a lens unlike any other. A single star or a single black hole creates a sharp, focused point of light, a phenomenon we call microlensing. A normal galaxy full of stars and gas creates a large, smeared and distorted image producing magnificent arcs and Einstein rings. A dark galaxy, however, would do something unique. Its lensing signature would be different. It would be a vast, extended and yet subtly grainy lens. The light from a distant quasar or galaxy passing behind it would not just be bent, but it would be fractured and scrambled by the individual gravitational fields of the millions of black holes within the structure, creating a distinctive flickering pattern of magnification, a lensing, scintillate lion that would be its unmistakable calling card. For the first time we had a map to the treasure. We knew what to look for. And with a new generation of sky surveys like the Vera C. Rubin Observatory designed to photograph the entire visible sky every few nights, with unprecedented depth and precision, we finally had the tools to conduct the search. The hunt for these phantoms, these galaxies of pure gravity, could now begin in earnest. The theoretical turning point had been reached, the stage was set, and the curtain was about to rise on a search for what could be the single, most profound and unsettling discovery in the history of astronomy. The ghosts were no longer confined to our equations. We were now preparing to see if they haunted the heavens themselves. And so a new cosmic beast enters the universal bestiary. A structure born not of light and fusion, but of collapse and silence. A ghost galaxy, a city of endings haunting the space between its luminous cousins. We have sketched its portrait in the language of physics, and we have walked its theoretical boulevards in simulations. But a ghost, no matter how exquisitely described, remains a figment of the imagination until it is seen, or in this case until its presence is profoundly felt. How then do we begin the hunt? How do you track a phantom made of pure gravity, an object whose entire existence is a vow of darkness? You cannot point a telescope at it and expect to see anything, for there is literally nothing to see. No, to find a galaxy of black holes you must learn to see the unseen. You must look not at it but through it. Our first and most powerful tool is a trick of spacetime itself, a phenomenon that turns the universe into a grand cosmic lens. Gravity, as Einstein revealed, does not simply pull on objects, it warps the very fabric of reality they inhabit. Light travelling through this warped fabric must follow its curves, and an object with the mass of a galaxy, even one devoid of stars, exerts a gravitational influence so colossal it becomes a lens of unimaginable power. Imagine holding a massive, imperfectly shaped piece of glass up to a distant starlit shore. The lights behind it would bend, stretch, and multiply. A single point of light might be smeared into a luminous arc, an Einstein ring, a perfect circle of ghostly light. Another might appear in 2 or 3 or 4 places at once, phantom images of a single distant quasar. This is gravitational lensing, and it is our primary signpost, the celestial fingerprint left by an invisible hand. Astronomers are masters at spotting these distortions. They scan the skies for these telltale signs of immense unseen mass, and they find them everywhere. These gravitational mirages are, we believe, the primary evidence for the vast halos of dark matter that cocoon every galaxy, including our own. So the challenge becomes one of differentiation. If you were to find a powerful gravitational lens, a region of space profoundly twisting the light from behind it, how could you possibly know whether you were looking at a conventional cloud of exotic dark matter particles, or our far stranger quarry, a concentrated swarm of black holes? The answer lies not in the broad stroke of the lens, but in its texture, its fine detail. A halo made of trillions of tiny diffuse particles would be gravitationally smooth. It would act like a perfectly polished, albeit curved piece of glass. The light it bends would be warped cleanly, elegantly. But a galaxy of black holes is anything but smooth. It is a granular, clumpy, gravitationally violent place. While the collective mass of its millions of singularities creates the grand overarching lens, each individual black hole acts as its own tiny flitting microlens. Think of it as looking through a pane of glass that has been peppered with buckshot. The overall image is still bent, but it is also riddled with countless tiny shimmering distortions. As these millions of black holes drift and orbit within their dark halo, these microlenses would flicker and dance. A distant lensed star wouldn't just be stretched into a static arc. Its light would subtly, erratically, and continually tremble. Its brightness would flicker not because of any change in the star itself, but because these gravitational bullets are constantly passing in front of it, momentarily focusing and scattering its light. The effect would be a kind of gravitational scintillation, a cosmic shimmer in the lensed image. Observing this effect would require unprecedented patience and instruments of breathtaking sensitivity. We would need to stare at a suspected lens for years, even decades, watching for that subtle, chaotic flickering, the signature of a structure that is not a cloud but a swarm. It would be the first tangible clue that we are looking at a fundamentally different kind of darkness. But lensing only reveals how the ghost galaxy affects the far distant universe. To gain a more intimate portrait, we must look closer at its immediate neighbourhood for evidence of its victims. A black hole galaxy is a predator. Its immense concentrated gravity is a weapon, and like any predator, it leaves a trail. Imagine a small innocent dwarf galaxy, or a globular cluster of stars wandering through the intergalactic void. By chance, its billion-year journey brings it too close to the edge of our invisible phantom. It would feel the pull of gravity just as it would with any galaxy. But this is different. There are no luminous spiral arms to welcome it, no galactic disk to merge with. There is only a cold, relentless, and unforgiving gravitational tide. The side of the star cluster closer to the dark galaxy, would be pulled with incomprehensibly greater force than the side farther away. This tidal force would begin to stretch it to tear at its edges. Stars that were once bound together by their mutual gravity for eons would be mercilessly stripped away one by one. The process is a kind of celestial unravelling. Picture pulling a single thread from a ball of cosmic yarn. This thread, a stream of liberated stars, would be pulled into a vast sweeping orbit around the invisible mass, a luminous ghost, tracing the path of its captor. This is a stellar stream, and we have seen them before. Our own Milky Way has draped in them the shredded remains of dwarf galaxies it consumed long ago. They are beautiful ethereal rivers of stars, some stretching for hundreds of thousands of light-years across the sky. Finding such a stream in the void with no visible galaxy at its centre would be a profound discovery. It would be like finding footprints in the snow leading to nowhere. You would know with chilling certainty that something was there, something massive enough to tear a galaxy apart. By mapping the exact trajectory of these stolen stars, by measuring their speeds and their chemistry, we could begin to map the shape and mass of the unseen object they orbit. We could calculate its density, its gravitational profile, and once again the granular nature of a black hole galaxy would leave a unique signature. A smooth, dark matter halo would create a smooth, coherent stellar stream, but a stream orbiting a swarm of black holes would be agitated. The individual gravitational kicks from the thousands of massive singularities passing near the stream would perturb the star's orbits. It would heat the stream up, puffing it out, making it wider and more diffuse than it should be. It might even create gaps and clumps within the stream, evidence of close encounters with these wandering monsters. The stream would not be a serene river, but a turbulent one, a scar left behind by a uniquely violent encounter. It would be another piece of the puzzle, a second witness testifying to the phantom's nature. The warped light from behind and the stolen stars from beside two lines of evidence pointing to the same dark heart. Yet both of these methods, for all their power, are circumstantial. They are shadows, echoes, footprints. They tell us something massive and dark is there, and they might even hint at its clumpy nature, but they do not allow us to hear its voice. To do that, to get the one piece of irrefutable smoking gun evidence we need to abandon light entirely, we must close our eyes to the electromagnetic spectrum and learn to listen to the vibrations of space-time itself. We must listen for the sound of gravity. Inside the crushing darkness of a black hole galaxy, the silence is a lie. It is, in fact, the most sonically violent place in the cosmos. Not sound in the conventional sense, of course, but a constant churning storm of gravitational waves. Every starless sun in this ghost galaxy is locked in a complex orbit, a gravitational dance, with its thousands upon thousands of neighbours. They swing past each other, they circle in binary pairs, they form chaotic triple systems. And every time they accelerate, every time they swerve or orbit, they shed a tiny amount of their energy into the universe as ripples in the fabric of space-time. For most of these orbits, these waves are a faint continuous murmur, a low-frequency hum of 1 trillion tons of matter in motion. But this is merely the background noise. The true symphony begins when two of these black holes find themselves trapped in a decaying orbit, a gravitational death spiral. Drawn together over millions of years, two black holes, each perhaps 30 times the mass of our sun, begin their final waltz. They are now spinning around each other hundreds of times a second, moving at a substantial fraction of the speed of light. The space around them is no longer a placid backdrop. It is a furiously twisting vortex. In these final moments, they are pumping out gravitational waves with more power than all the shining stars in all the galaxies in the observable universe combined. This is not a whisper. It is a cosmological scream. As they spiral closer and closer, the frequency of these waves rises, and so does their amplitude, creating a characteristic signal that scientists call a chirp. It's a sound that sweeps upwards in pitch and volume, a cosmic glissando that culminates in a final percussive bang as the two event horizons touch and merge into one. A new, more massive black hole is born, and the space-time around it violently rings like a struck bell before settling back into silence. Our gravitational wave observatories like LIGO and Virgo have already heard these chirps. They are the sounds of individual pairs of black holes merging somewhere out in the vast emptiness of the universe. We detect one every few days, but a galaxy of black holes would be entirely different. It wouldn't produce just one chirp. With millions of black holes packed into a relatively small volume, mergers would be a common, almost daily occurrence. This structure would not be a source of occasional isolated signals. It would be a beacon, a lighthouse of gravitational waves broadcasting a continuous overlapping chorus of chirps. It would be a stochastic background, a persistent hum of spacetime vibrations punctuated by the loud cries of the most recent, most powerful mergers. A conventional dark matter halo composed of elementary particles cannot do this. WIMPs and axions do not form binary pairs and merge. They do not scream out in the language of gravity. They are for all intents and purposes gravitationally silent. This unique thunderous signature is the key. It is the one piece of evidence that cannot be explained away. Future space-based gravitational wave observatories like the Laser Interferometer Space Antenna or LISA will be tuned specifically to listen for this cosmic symphony. LISA, with its millions of kilometers-long arms, will be sensitive to the lower frequency gravitational hum produced by the slow majestic dance of countless black hole pairs long before they enter their final frantic merger. It would be able to pinpoint a region of the sky that was anomalously, impossibly loud in gravitational waves. Imagine scanning a radio dial, searching through static, and suddenly discovering a powerful, persistent broadcast station where there should be only silence. That is how we will find them. We will hear their collective voice ringing out across the cosmos. So now we have our complete forensic toolkit. First, we will search for the gravitational lens, a great invisible anchor distorting the fabric of the universe, and we will watch for the telltale shimmer in the lens light that betrays the swarm within. Second, we will hunt for the victims, the ghostly stellar streams, the luminous scars that trace the phantom's path through the void, looking for the turbulence kicked up by its dark heart. And finally, the ultimate confirmation, we will turn our gravitational ears to the sky and listen for the symphony of a million black holes merging a chorus of space-time chirps that no other object can produce. Each piece of evidence on its own is tantalizing but ambiguous. But together, the warped light, the stolen stars, and the gravitational song, they form an undeniable trinity of proof. They provide a path out of the realm of pure theory and into the world of observation. The ghost at last can be cornered. The implications are staggering. To confirm the existence of even one such galaxy would not just add a new creature to our cosmic zoo. It would force us to re-evaluate the very dawn of the universe. It would provide a radical alternative solution to the dark matter mystery, and it would open up a new terrifying window into the ultimate fate of matter in the cosmos. The theoretical groundwork has been laid. The observational strategy has been devised. The hunt is no longer a distant dream, but an impending reality. The only question that remains is a simple yet profound one. As our next generation of telescopes and observatories begin their patient vigil, scanning the silent, empty patches of the sky, where exactly should we begin to look? And so we stand at a precipice of understanding. We have gathered the whispers from the dawn of time, the theoretical spectres of primordial black holes. We have faced the profound and unsettling silence from the frontiers of physics, where our most cherished theories of matter simply fail to account for the universe we see. The pieces are on the board, scattered and tantalizing. Now is the moment to assemble them, to step away from conjecture and into the realm of rigorous creation. It is time to build from the raw mathematics of gravity and the quantum chaos of the first second, a cohesive and terrifyingly plausible vision, the architecture of a galaxy made of pure darkness. The construction does not begin with the gentle collapse of a luminous nebula, but in the violent, seething cauldron of the post-inflationary universe. Imagine a cosmos less than a second older place of such unimaginable density and energy that the very fabric of space-time buckled and churned like a stormy sea. In this maelstrom, as we explored microscopic pockets of reality, could become so compressed they collapsed directly into black holes, not from the death of a star, but from the raw, untamed energy of creation itself. These are our building blocks, the primordial black holes, or PBHs, scattered like a fine dark dust throughout the expanding volume of space. Unlike the gas and dust that would later form our own galaxy, this material does not glow, it does not radiate, it does not interact with light or with itself through any force except the most ancient and inexorable one gravity. In the standard model of cosmology, tiny quantum fluctuations in the early universe are amplified by inflation, creating infinitesimally denser regions that act as gravitational seeds. Over billions of years, normal matter drawn by these seeds would fall inwards, heating up, igniting into a brilliant conflagration of starbirth that would eventually settle into the majestic spirals we know and love. But what if a region of space was seeded not only with a gravitational anchor, but was also overwhelmingly dominated by our dark dust of PBHs? The simulation begins. The cosmic clock starts ticking. Gravity blind and indiscriminate begins its work. The PBHs, each one a microscopic point of infinite density, feel the subtle pull of their neighbours. There is no gas pressure to resist the collapse. There are no stellar winds to blow material away. There is only the pure, cold, silent calculus of attraction. What the models show us is not a slow, graceful accretion, but a process far more frenetic and violent known as hierarchical clustering. Small clumps of a few dozen primordial black holes form first a frantic gravitational mosh pit in the dark. These small clusters, now possessing a greater collective gravity, hurtle through the cosmic void, sweeping up more lone PBHs and colliding with other clusters. The process is a cascade, an avalanche of darkness. 1,000 points of gravity become a million become a billion, all coalescing into a single swarming halo. It's a city being built without a single light, its architecture defined only by the invisible scaffolding of spacetime itself. Without the complex feedback loops of astrophysics, supernova explosions, radiation pressure, magnetic fields, the formation of this phantom galaxy is brutally efficient. There is nothing to halt the inexorable pull inwards. The structure that emerges from these supercomputer models is both alien and strangely familiar. It possesses a dense central core and a more diffuse sprawling halo just like the Milky Way. Yet, it is a ghost image, a photographic negative of a galaxy. Where we would expect a brilliant star-forming nucleus, there is only the most extreme concentration of mass, a place where the density of black holes becomes so great that spacetime itself is warped into a treacherous labyrinth. This brings us to the most critical question, one that haunted early theorists for decades. How could such an entity possibly be stable? Surely an object composed entirely of gravitational sinks would be a cosmic time bomb doomed to an immediate and catastrophic collapse. The black holes drawn by their mutual attraction should all rush to the centre and merge into one impossibly vast supermassive black hole. The galaxy would simply devour itself in an instant of cosmic history, but the universe, especially when governed by the intricate dance of gravity, is rarely so simple. The key to its survival, the secret to its eons-long lifespan, lies in a phenomenon called violent relaxation. As the primordial black holes fall towards the burgeoning galactic core, they don't simply plummet straight in. They engage in a chaotic, high-speed gravitational ballet. In a series of breathtakingly complex 3-body, 10-body, 1,000-body interactions, they exchange momentum and energy. Like billiard balls on a warped table, they slingshot past one another. Some are kicked into higher, more distant orbits in the halo, losing energy. Others are thrown violently inwards, gaining that very same energy, only to be flung out again by another close encounter. This process is a fierce and efficient mechanism for redistributing energy throughout the system. It prevents a runaway collapse. Instead of a single monolithic entity, the galaxy finds a state of dynamic equilibrium. It becomes a self-regulating system, a gravitational gyroscope of staggering proportions. The core remains incredibly dense, a seething swarm of black holes in tight frenetic orbits. But the halo remains vast and stable, its inhabitants held in a delicate balance between their inward pull and the orbital velocity they gained during that initial violent relaxation. The galaxy does not consume itself. It learns to live with its own infinite appetite, caging its own voracious nature within a stable, invisible architecture that could persist for trillions of years. Imagine floating in the heart of this metropolis. There is no starlight, no nebulae, no planets. The only sensation is the silent, powerful tug of gravity shifting and pulling from every direction at once. The darkness is not empty, it is full. It is a palpable presence, the weight of 1 trillion collapsed worlds. It is a structure of pure geometry of warped spacetime, a silent, enduring monument to the power of gravity unleashed. Here in this ghost galaxy, the universe's most destructive objects have become the building blocks of its most stable and massive creations. And within this stable, silent city, a slow, patient, and constant form of violence is always unfolding. While the galaxy as a whole is in equilibrium, the lives of its individual citizens are not. In the crushing density of the core, and even in the sparser regions of the halo primordial, black holes are inevitably finding each other. Two black holes, perhaps born fractions of a second apart at the dawn of time, might spend 13 billion years in a slow, graceful dance across the galactic stage, their orbits gradually drawing them closer. This is the gravitational waltz. For eons they circle locked in an invisible embrace. But this is not a perpetual dance. With every pass they radiate a tiny amount of energy, not as light, but as ripples in the fabric of space-time itself, as gravitational waves. This slow bleeding of energy is the relationship's death knell. It seals their fate. As they lose energy, their orbits shrink. They spiral closer and closer, faster and faster. The slow waltz becomes a frantic tango, then a violent, inescapable vortex. In the final milliseconds of their existence as separate entities, they are whipping around each other at nearly the speed of light, warping spacetime so violently that the waves they emit become a crescendo, a cosmic scream that travels across the universe. Then silence. They merge. A single, slightly larger black hole remains its surface quivering like a struck bell, shedding the last vestiges of the collision as a final burst of gravitational waves before settling into the eternal quiet of the phantom city. This is the only form of activity this galaxy knows. Not the light of a supernova, but the shudder of spacetime. Not a stellar flare, but the final violent union of 2 points of eternal darkness. And this is not a rare event. In a galaxy populated by a quadrillion of these objects, these mergers are happening constantly. Not one or two, but thousands, perhaps millions at any given moment. Each one is a tiny solitary whisper in the dark. Alone they are undetectable from our vantage point millions of light years away. But together they create something extraordinary. Together they produce the galaxy's voice. They combine into a choir that sings the song of dark matter, a symphony of silence. This symphony is the key. It is the definitive, unambiguous smoking gun we have been searching for. To hear it, we don't need a telescope that sees light, but an observatory that can feel the very vibrations of reality. Instruments like the future laser interferometer, space antenna or LISA, a celestial triangle of spacecraft millions of kilometers on a side, are not designed to look at the sky, but to listen to it. They are engineered to detect the infinitesimal stretching and squeezing of spacetime caused by passing gravitational waves. When we finally deploy these next-generation detectors, we will be able to hear the individual high-frequency chirps from the mergers of massive stellar-born black holes in normal galaxies. We have already accomplished this, a revolution in astronomy. But the ghost galaxy will sound completely different. It won't produce a series of distinct, isolated chirps. Instead, the millions of simultaneous quieter mergers of its smaller primordial black holes will blend together. They will create a persistent underlying hum across the cosmos, a stochastic gravitational wave background. This is the spectral fingerprint of a phantom galaxy. It is a unique signature encoded in the language of gravity itself. The models predict a very specific spectrum of frequencies for this background noise. The frequency depends on the mass of the primordial black holes, and the amplitude, the sheer volume of the hum, depends on their density and merger rate. Finding a gravitational wave background is one thing, but finding one that perfectly matches the precise calculated predictions for a self-annihilating dark matter galaxy, that would be irrefutable. It would be like standing in a silent room and suddenly hearing the unmistakable ambient hum of a distant unseen city. We would have heard the voice of the invisible. But the cosmos may offer us an even more direct visual confirmation, a way to trace the outline of the ghost itself. The evidence would come from a different kind of observation, one based on the most fundamental prediction of Einstein's theory of relativity, that mass bends light. An object as massive as a galaxy creates a profound warp in the space-time around it, acting as a colossal natural telescope known as a gravitational lens. We see this all the time. The gravity of a massive galaxy cluster in the foreground will bend and magnify the light from a far more distant galaxy behind it, creating beautiful distorted arcs and multiple images of the background source. Now imagine we point our future telescopes at a distant quasar. We see its light is being warped. We see the classic signs of a powerful gravitational lens at work, magnifying and smearing the quasar's image into an Einstein cross or a luminous ring. Standard procedure would be to then take a deep field image to study the massive galaxy. We know must be sitting in the foreground the object whose gravity is bending the light. But in this case, when we look, we would find nothing. Absolutely nothing. No stars, no gas, no dust. Just an impossibly perfect, impossibly empty patch of black sky, sitting exactly where 1,000,000,000,000 solar masses of matter ought to be. We would be staring at a lens made of pure, invisible mass. We would have photographed the shadow of a ghost. This discovery, a dark lens of immense power, would provide the spatial coordinates, the where, to complement the gravitational wave signal's what. And it gets even more specific. Future precision astrometry missions charting the exact positions and movements of billions of stars could detect an even subtler effect. As our line of sight to a distant star passes through the halo of this phantom galaxy, the individual primordial black holes, though tiny, would each act as a microlens. They would cause the background star's light to momentarily flicker, to brighten and dim, in a characteristic way that can be distinguished from intrinsic stellar variability. A normal galaxy's dark matter halo, if made of undiscovered particles, would be a smooth distribution of mass and would produce no such effect. But a halo made of countless discrete massive black holes would create a faint constant and statistically unique twinkling in the stars that lie beyond it. It is the final piece of the puzzle. The gravitational wave background tells us the city is humming with activity. The dark macrolensing shows us precisely where the city is, and the widespread microlensing confirms that the city is indeed built from 1,000,000,000,000 discrete dark bricks. This is no longer a fever dream on a theorist's blackboard. We have moved beyond speculation and into the realm of a testable, falsifiable hypothesis. We have built a complete self-consistent model of a galaxy of pure darkness, from its violent birth in the primordial chaos through its long and stable life, as a gravitational gyroscope to the constant hum of its self-annihilation through black hole mergers. And for each stage, for each characteristic, we have identified a unique observable signature, a specific fingerprint that no other theory of dark matter can replicate. The theoretical framework is complete. The observational path is laid out before us. We now know exactly what we are looking for. We have drawn a map that leads to the shores of a new continent of cosmology, a dark shore we have until now only been able to imagine. The instruments that will allow us to read this map are being designed, built, and prepared for launch. We are on the verge of being able to not only ask the question, but to force the universe in no uncertain terms to give us its answer. We're ready to go hunting for ghosts. And so the silhouette of this impossible structure recedes into the darkness of our imagination. We are left with the lingering echo of a galaxy with no light, a phantom metropolis built not from the nuclear fires of suns, but from the silent, voracious pull of countless black holes. It is a concept that feels torn from the pages of mythology, a cosmic underworld charting its own gravitational destiny, utterly indifferent to the starlit universe we call home. To have walked the theoretical shores of such a place is to have fundamentally altered our perception of what a galaxy can be. We have been conditioned to see them as grand islands of light, luminous tapestries, woven with the brilliant threads of nebulae and the diamond dust of 1,000,000,000 stars. We associate them with radiance, with creation, with the very genesis of life-giving elements forged in stellar furnaces. Yet this dark sibling, this gravitational ghost, forces us to reconsider the most basic definitions we hold dear. It suggests that the universe is not only stranger than we imagine, but stranger than we can imagine. It posits that gravity in its most extreme and unadulterated form may be a sufficient architectural principle on its own. It whispers of a cosmos where the grandest structures might be utterly invisible, their existence betrayed only by the subtle ways they warp the light of things far beyond them, or by the faint mournful cries of gravitational waves shivering through the void. This journey into the heart of a theoretical abyss wasn't just an exploration of a bizarre cosmic object, it was an exploration of the limits of our own understanding. It challenged our reliance on light as the ultimate messenger of cosmic truth. For millennia we have been astronomers, star namers, our knowledge predicated on what we could see, but here we are asked to become something else entirely. We must become gravitational cartographers, listening for the tremors in spacetime mapping the unseen contours of a dark landscape. We must learn the language of absence to read the story, written in the bending of light and the subtle dance of distant galaxies. The black hole galaxy is more than a hypothesis. It is a profound philosophical provocation. It asks us what else is out there hidden in plain sight, veiled not by dust or distance, but by its own fundamental nature. What other cosmic architects are at work building structures from ingredients we have yet to name, following blueprints that defy our current physics. This phantom city of singularities serves as a powerful, humbling reminder that the universe has no obligation to make itself visible to us, no duty to conform to our aesthetic or intellectual expectations. It simply is in all its magnificent and sometimes terrifying diversity. Our speculative odyssey to this place did not begin here in the depths of pure theory. It began with a much more immediate and persistent cosmic enigma, a shadow that has stretched over astrophysics for nearly a century. We started with the gentle, almost imperceptible motions of our own cosmic backyard, with the stars on the outskirts of galaxies like our Milky Way. We saw them moving too fast, orbiting with a speed that defied the visible matter we could account for. It was as if a powerful unseen hand was gripping the galactic disk, refusing to let its stellar children fly off into the intergalactic void. This was the first great clue, the first tug on a thread that would lead us to the most outlandish of possibilities. We called this unseen influence dark matter, a name that perfectly captured both its mysterious nature and our profound ignorance. It was a placeholder for a discovery yet to be made, a cosmic X in the grand equation of the universe. For decades, the search for the particle or particles of dark matter has been a central drama in modern physics. We have built vast sensitive detectors deep underground, shielded from the cosmic ray noise, waiting patiently for the whisper of a WIMP, a weakly interacting massive particle, to finally reveal itself. We have pointed our most powerful telescopes at the sky, hunting for the faint signature of its annihilation, a flash of gamma rays that would signal the end of a long and frustrating search. But the underground caverns have remained silent. The sky has offered no definitive confirmation. The shadow of dark matter has only deepened, its gravitational effects more precisely mapped, yet its fundamental identity as elusive as ever. It was this enduring mystery, this persistent silence from the particle world, that forced scientists to pivot, to turn their gaze toward a more radical and in some ways more elegant solution. What if dark matter wasn't a new exotic particle at all? What if it was something we already knew existed, something born in the most extreme conditions imaginable? This question led us back in time to the very first moments after the Big Bang. In that cauldron of unimaginable energy and density, before the first atoms had even formed, tiny fluctuations could have caused pockets of the nascent universe to collapse directly into black holes. These would not be the stellar remnants we are familiar with, the corpses of giant stars. These would be primordial black holes forged from the raw stuff of creation itself, a population of ancient silent wanderers scattered throughout the cosmos before the first star ever ignited. Suddenly the puzzle pieces began to fit together in a new and startling way. These primordial black holes would be gravitationally powerful, yet electromagnetically invisible. They would not interact with light. They would not decay. They would be the perfect candidate for the universe's missing mass hiding in plain sight. And once we allowed for that possibility, once we accepted that the universe might be filled with these ancient dark seeds, the next logical step, however audacious, became unavoidable. If they could account for the missing mass within a normal galaxy, could a vast swarm of them under the right conditions form a galaxy of their own? This was the final breathtaking leap of imagination. From a subtle anomaly in stellar orbits through a frustrating search for an exotic particle to the fiery crucible of the Big Bang, we arrived at the concept of a structure of pure gravity, an entire galaxy made of nothing but primordial black holes. We traced a single thread of logic from a mundane observation to a mind-bending conclusion, a testament to the power of the scientific method to lead us to shores we never intended to find. It's a journey that showcases how science progresses, not just through steady, incremental discoveries, but through bold, paradigm-shifting acts of imagination by daring to ask, what if? But this grand, dark architecture, however logically sound, remains a ghost in the machine of theory. It is a beautiful and compelling mathematical object, a solution to a long-standing cosmological problem, but without observational evidence it is little more than an elegant fiction. To drag this phantom out of the shadows and into the light of scientific consensus, we need more than imagination. We need new eyes. We need new ears. We need to build a new generation of observatories designed not just to see the universe, but to sense it in fundamentally new ways. The quest to confirm or deny the existence of a black hole galaxy is already driving a technological revolution, pushing our engineering and data processing capabilities to their absolute limits. We are standing on the cusp of an era where we might finally have the tools to map the invisible. Consider the successors to the Hubble and James Webb Space Telescopes, future observatories with mirrors so vast they will be able to detect the most subtle distortions in the fabric of space. A galaxy made of black holes would be invisible to them, directly a complete and utter blank spot on the sky. But its gravitational influence would be profound. As light from a far more distant luminous galaxy travels towards us, passing through the domain of this dark structure, its path would be bent, warped, and magnified. We call this phenomenon gravitational lensing. With current technology, we can see the dramatic arcs and rings created when light passes by a single massive galaxy cluster. But the next generation of telescopes will be sensitive enough to detect something far more subtle, the collective faint lensing signature of millions of smaller planet mass objects. They would be looking for a specific kind of cosmic flicker, a micro-lensing storm where the background light of a distant galaxy appears to subtly twinkle and shift as it passes through a vast field of compact invisible masses. It would be an unmistakable fingerprint, a pattern of distortion that could not be created by a smooth cloud of hypothetical particles, but only by a massive collection of discrete point-like objects. Finding such a signal would be the astronomical equivalent of seeing footprints in the snow, proof that something unseen had passed that way. We would not be seeing the black hole galaxy itself, but its gravitational shadow cast across the cosmos, a silhouette traced in the warped light of a galaxy billions of light-years behind it. It would be the first truly tangible piece of evidence, a signpost pointing us toward this new and hidden cosmic geography. Yet light is only half of the story. The true revolution in our ability to probe these dark realms comes from our newfound ability to listen to the universe. For most of human history, astronomy has been a silent movie. But with the advent of gravitational wave observatories like LIGO and Virgo, we have finally turned on the sound. We can now hear the cosmic cataclysms, the violent collisions of black holes and neutron stars as they send ripples, gravitational waves shuddering through the fabric of space-time itself. These ground-based detectors are exquisitely sensitive to the mergers of stellar mass black holes, the final chirping cries of dying binary systems. They have opened a new window onto the cosmos, but their vision, or rather their hearing, is limited to these high-frequency events. To hunt for a galaxy of primordial black holes, we need a different kind of ear. We need to listen for a much lower, deeper frequency, the slow, inexorable in-spiral of more massive black holes, the kind that might form the central core of a dark galaxy. This requires an observatory of truly astronomical proportions. This is the promise of LISA, the Laser Interferometer Space Antenna. LISA will not be a single observatory on Earth, but a triumvirate of spacecraft flying in a precise formation, millions of kilometers apart, trailing our planet in its orbit around the Sun. They will be connected by laser beams, forming a gravitational wave detector of unprecedented scale and sensitivity. LISA will be a cosmic seismograph capable of sensing the faintest low-frequency tremors in the universe. It will be able to hear the slow, gravitational hum of supermassive black hole binaries in the centers of distant galaxies, a process that takes millions of years to unfold. And crucially for our search, it would be perfectly tuned to detect the mergers of intermediate mass black holes, the very building blocks from which a dark galaxy might be constructed. If such a galaxy exists, it would not be a silent place. It would be a dynamic, chaotic environment, a gravitational dance floor where its constituent black holes are constantly interacting, pairing up, and eventually merging. These mergers would produce a unique chorus of gravitational waves, a continuous overlapping symphony of chirps and tones at the exact frequencies LISA is designed to hear. If we were to point a future, more advanced gravitational wave observatory in the direction of a suspected dark galaxy, one identified through its lensing signature, and we heard this characteristic cacophonous hum, it would be the smoking gun. It would be the sound of the invisible city, the ambient noise of a metropolis of singularities, confirming one of the most audacious predictions in the history of science. So what if after all this searching, after decades of meticulously scanning the sky for faint distortions and listening intently for the whispers of space-time, we find nothing? What if the lensing signatures never appear and the gravitational wave spectrum remains stubbornly silent? Would this entire intellectual journey have been a failure, a grand and entertaining diversion into science fiction? Absolutely not. The value of a powerful scientific idea is not measured solely by whether it turns out to be true. Its value also lies in the questions it forces us to ask, and the new avenues of research it opens up. The very act of seriously considering a galaxy of black holes has forced us to refine our models of galaxy formation, to reconsider the physics of the early universe, and to design and build these incredible new instruments that will undoubtedly uncover wonders we cannot yet foresee. Science is not a straight path to a single truth. It is a process of exploration, of charting a vast and unknown territory. Sometimes we draw a feature on the map that upon closer inspection turns out not to be there. But in the process of searching for it, we map the surrounding landscape with exquisite, unprecedented detail. We learn about the real mountains and rivers and valleys that we would have otherwise overlooked. The hypothesis of a black hole galaxy has served as a whetstone, sharpening our theoretical tools and our observational capabilities. It has pushed our understanding of gravity cosmology and structure formation to their absolute limits. Even if they don't exist, the legacy of this incredible idea will be a far deeper and more nuanced understanding of the universe that does. It provides a crucial null hypothesis, a benchmark against which we can test our other theories for dark matter and galaxy evolution. We stand at a remarkable moment in our cosmic journey. We have for the first time built tools that are not limited by the visible spectrum. We are transcending our biological reliance on light and learning to perceive the universe through the fundamental force of gravity itself. We are in essence developing a new sense, one that will allow us to perceive the hidden cosmic architecture, the dark scaffolding upon which the luminous universe is built. The coming decades promise a flood of new data, a new map of the heavens drawn not in the ink of photons but in the subtle curvature of space-time. On that map we may find signposts that point the way to these phantom galaxies, these silent monuments to the power of gravity. Or we may find something else entirely, something even more strange, more beautiful and more challenging to our conception of reality. And that ultimately is the point. The universe is not a solved puzzle. It is a grand, unfinished symphony, and we are just now learning how to hear all the instruments. Our journey from the familiar star-strewn shores of the Milky Way to the theoretical heart of a galaxy made of black holes is a testament to the most powerful force we know, human curiosity. It is the engine of science, the restless urge to look over the next hill, to peer deeper into the darkness, and to ask the most profound and audacious questions we can muster. What else is out there? What other forms can matter and energy take? What grand cosmic principles have we yet to uncover? The search for a galaxy of black holes is more than a search for a single exotic object. It is part of our ongoing quest to understand our place in the cosmos, to read the unwritten chapters of the universe's history, and to marvel at the infinite breathtaking beauty of its deepest secrets. The darkness is not empty. It is simply a story waiting to be told.